Hi, welcome to the basics of cationic curing. My name is Mike Idacavage, and I'm an advisor to Nagase Specialty Materials. In today's webinar, I'm looking to give a good broad overview of the basics of cationic curing. As you can see on the agenda for today's presentation, I'm going to touch upon multiple topics. I'll start with an introduction to UV curing, followed by a brief discussion on the mechanism of cationic curing. Then I'm going to move into the areas of what materials are used in cationic curing, and these will be epoxides, polyols, various additives, and photoinitiators. We'll then get into formulating strategies. So how can you use these on a practical basis? I'd like to follow that by giving a little bit of an overview into a really interesting aspect of cationic curing, and that's in hybrid systems. And I'll end up with some examples of cationic formulations so you can see how they're used on a practical basis for commercial applications. While cationic curing is used in a wide range of coatings, inks, and adhesives, I would like to start first with understanding some of the basic chemistry of cationic curing. So what is UV or EB curing? And basically it's using UV energy, visible light, or low energy electron beam as opposed to thermal, evaporative, or oxidative, air dry type curing to form a coating, film, or ink. The types of energy that is used for energy curing tend to be UV, and this is between the 200 and 400 nanometer range. Visible light, 380 to 700 nanometers is considered the common range for that. Or electron beam, and this is using low energy electron. Note that I'm going to be using UV curing or UV-EB curable or radiation curable or energy curable terms, and these and you'll hear these out in the industry, and they can be used interchangeably. In UV curing, the most common energy source is UV energy between 200 and 400 nanometers. So what is the UV curing process? On this slide, I have a comparison between conventional cure and UV curing. In conventional cure, and this is something we're all very used to seeing, it's basically watching paint dry. You have your wet application here, and you lay it down at a certain thickness. It then goes into a drying stage. This is to remove the solvent. It allows the coating to coalesce, and you use heat or forced air to dry it. Now, drying time can be seconds or minutes. And what you get is a reduction in the thickness of the coating, and you get your dry film. And the properties tend to develop over time. In UV curing, the first step is essentially the same. You apply your formulation, wet application, using the same coating technology used for conventional cure. It could be spray, it could be roller coat or curtain coat, or a wide range of coating applications. However, it's the next step where things become quite different. It gets exposed to UV energy or electron beam, and you get instantaneous cure for the most part, or at least initial cure. It starts a reaction. However, in cationic cure, this will actually extend quite some time after the initial cure. And I'll speak about that in one of the following slides. However, you get your dry film, and what's important to notice is that the thickness stays the same because you're not losing any solvent. You get some very good quick property developments. However, and immediate if you're using free radical, it's a bit slower if you're using cationic. You get a high cross-link density, and you retain the shape of the coating. Many of us are very familiar with free radical curing when it comes to UV curable coatings, inks, and adhesives. In free radical curing, you get polymerization through double bonds. So you start out with an acrylate or a methacrylate. double bond, and these are the ones that tend to polymerize once you form the free radical. Cationic curing is a bit different. In this case, you get polymerization through epoxy groups. Cycloaliphatic epoxies tend to be the most commonly ones used. In free radical curing, when using UV as the energy source, you have a photoinitiator that absorbs the UV light and generates a free radical. These free radicals react with double bonds, causing chain reaction and polymerization. However, in a cationic curing, it's similar, but not exactly the same. You use a photoinitiator, just like you do in free radical, and this photoinitiator absorbs the UV light and generates, instead of a free radical, a Lewis acid. So you generate that acid, and that acid reacts typically with epoxy groups, resulting in the polymerization. So instead of having free radical generating your polymerization, you rely on forming a Lewis acid. So now that you know the difference, let's take a very brief dive into the mechanism of cationic cure. As mentioned earlier, cationic curing is initiated by the application of UV energy. What is a little bit different in the case of cationic cure is that heat can also play a role in the mechanism. As we see here on the slide, we'll start out with our UV energy here application. The photoinitiator is exposed to that energy, and here we have a hexafluoro initiator, and we'll cover these a little bit later in some more detail. So this fragments, forms a cation, and now we have just a real simple epoxy here for this example. So the cation reacts with the epoxy, and you get ring opening, forming another cation. And as you can see now, this will serve to propagate by reacting with a second epoxide, and we see the start formation of the polymer chain here. Once that initial cation is formed, it will continue to react with other epoxides in the formulation and build up our polymer chain. They'll just keep reacting, and you get your coating, your ink, so forth. For the listeners who have some experience in other types of chemistry, you'll probably recognize this as a very classic acid-catalyzed epoxide reaction. And for those of you who are familiar with that type of reactions in chemistry, you also realize that you can get something called dark cure. So what is dark cure? When the UV light is stopped, the polymerization reaction will continue, and it will just keep going until it gets terminated in some form. This is commonly called dark cure, and it can take place, ironically, in the presence of visible light. It's now only dependent on the presence of the cations that are formed. Another term that you may hear out in industry is post-cure for this phenomenon. This can be accelerated by heating after exposure to UV light, so you can shorten that the time for dark cure just by warming up your coating or your ink. Hydroxy-functional materials are commonly used in cationic curing formulations. If you do have them in your system, you can get chain transfer occurring. And so basically, as you see in this case, here we have our hydroxy compound, and this is the polymer chain that's been forming. You can get the transfer. Basically, it stops this chain from growing and moves on and potentially starts a new chain. So you can get lower molecular weight polymers formed. And finally, all good things will come to an end, and you can get chain termination. Here we have again our polymer chain. In this case, it reacts with an anion, part of the photoinitiator package, caps the polymer formed, and your polymer is now stopped. Rather than spreading out the mechanism over multiple slides, here's a very quick summary, a one-page, actually a one-slide summary of a cationic polymerization mechanism. So this is just what we've covering over the last few minutes, starting out with these monomers here, and you have your initiation with the photoinitiator, forms a cation, and this starts, in this case, starts growing. You get your propagation step, and then finally, with the nucleophile, a termination step. I'd like to move on from the mechanism of cationic curing, and now take a step back and become a little bit more practical in everyday cationic curing, and look at what materials are used to make use of the good properties of cationic cure. Like other types of curing, such as free radical curing, one does not usually have a single or even a double component system to get the coating or ink or adhesive that you're looking for. UV curing cationic systems tend to have multiple components, so that you formulate those to get the exact properties and or cure speed that you're looking for. And what I have here illustrated on this slide is a generic typical formulation for cationic curing. The bulk and basic coating properties come from a epoxide, and these typically are cycloaliphatic epoxides. So they give you your basic curing properties. You have polyols in the system for cross-linking to give some flexibility. Though there may be epoxy, other epoxy or vinyl ether monomers for viscosity reduction. These tend to be very low viscous materials, so you'll lower your viscosity, for example, if the requirements of your application equipment need something that's low, such as inkjet. Additives to tune your performance, and we're talking pigments, things like that. And of course, a photoinitiator package. These generate your cation, and these tend to be commonly sulfonium salts. So these are combined, mixed, exposed to UV energy, and you get your cured product. Electron beam can also be used to cure cationic formulations, and as we can see here, it's very similar to UV curing. You have your cycloaliphatic epoxides for your coating properties. You use polyol. You may have epoxy or vinyl ether. You have additives, but unlike free radical electron beam curing, you need a photoinitiator package. These will be are needed to generate your cation, because just exposure of the chemistry, epoxide chemistry, to electrons will not form easily cations. So you need to generate your cations and use that by a photoinitiator. And these tend to be iodonium salts. Now, this actually, electron beam curing is rather unusual. In a 30-plus year career of doing UV curing and electron beam curing, I've only had one project that I saw that used electron beam cationic curing. So I wanted to put it in here so you know it can happen, but it's actually quite rare. Let's talk about the materials themselves. I mentioned that epoxides tend to be the most common material that's used to give the base properties, and the class of materials that are used tend to be cycloaliphatic epoxides. These are a major component of the formulation by weight. They are also the major contributor to the properties of the cured photopolymer. They can be comparable to oligomers in free radical UV curable formulations. The workhorse epoxide most commonly used is this cycloaliphatic epoxide shown on this slide. The trade name for this material is siloxide 2021P, and it has a low viscosity. So at room temperature, 250 millipascals, typically in a low color, low odor, easily obtainable and high purity. It's very highly reactive. There's no oxygen inhibition when you're using this material. It has low shrinkage, excellent adhesion to metals and plastics, a high gloss, and excellent electrical properties. So this epoxide, cycloalpha epoxide, is by far and away the most commonly used. I've seen numbers giving it between 85 and 90% of cationic cure formulations using this particular epoxide, and I think based on my experience, I believe that number. There are other cycloaliphatic epoxides that can be used, and I have a few of them listed here on the slide. For example, siloxide 2081 and gives increased flexibility of the cured coating, and you can see that is likely due to that aliphatic chain here in the middle. Similarly, Epilede GT401 will give good flexibility again with the same structure. If you need a high T sub G, you can have EHP 3150. This forms a very good, highly cross-linked material. Perhaps you need a dual cure, one where you want to combine a free radical system with a cycloaliphatic or a cationic cure system, and cyclomer M100 will give you those properties. Other commonly used cycloalpha epoxides are siloxide 2000 and siloxide 3000. In addition to cycloaliphatic epoxides, non-cycloaliphatic epoxides can be used. Here we see on this slide 3 different types of non-cycloaliphatic epoxides that give increased toughness, such as HBE 100, Epifriend here, or simply an epoxy phenol Novolac. If you need increased flexibility, this Epilede PB series type system will give those properties. So now you can see where you can fine-tune the basic properties of your cured system. With that relatively wide range of epoxides that are used in cationic curing, you may be asking yourself, why would cycloaliphatic epoxides be the dominant epoxide that it's used in cationic curing systems? And I think that is illustrated well in this slide here. This is work done by Professor Alex Scranton at the University of Iowa. And we can see here, and we have on the y-axis the conversion, x-axis the amount of time on after exposure to UV light, UV energy, where you start getting reaction. You can see the cycloaliphatic epoxide very quickly starts to cure, very fast reaction, and you get a quite high level of cure. Remove the from a cycloaliphatic to here this aliphatic with an aromatic group. We get the initiation starting about roughly the same time, but it's a much slower conversion rate. And finally, an aliphatic type, or so a non-cycloaliphatic type epoxide. Here we have a very slow initiation versus almost immediately. This is now taking 40 to 50 seconds to start, and it's just a very slow curing rate. So you can see why, in addition to all the physical properties you get from this cycloaliphatic epoxides tend to be the epoxide of choice for us. In addition to cycloaliphatic epoxides, there's another type of structure that's been quite popular to use in UV curable cationic curing, and that's those that use the oxetane structure. So we see our general, I have an illustration, a cartoon here of a general structure for an oxetane, and you can notice its similarity to cycloaliphatic epoxides. This gives an excellent combination of hardness and flexibility. You get very good adhesion, great solvent resistance, good abrasion resistance, and less shrinkage than cycloaliphatic epoxides. So it becomes now it's becoming a really important tool in a cationic curing formulator's tool chest. Here are some examples of oxetane structures that are commonly used in industry. We have EHO, so really simple system here. H-box, a little bit larger system here. OX-IPA and OX-BP, so much larger systems. You get different properties there, of course, and OX-MA. So you're not restrained to using just a single oxetane. There's a selection, and all of these will give you slightly different properties. What are some of the advantages of oxetanes compared to epoxides? So what are people looking at them? They tend to be or can be maybe at a slightly higher cost than the workhorse epoxide, but there are reasons people use these. And some of these are listed on these slides. You get potentially lower skin and eye irritation, lower sensitization, a lower potential for mutagenesis, lower toxicity, and little or no odor. Some other common epoxy monomers that are used in cationic curing are siloxide 2000, limonene monoxide, and limonene dioxide. And of course, the last two, both limonenes, can be derived from some natural sources. In addition to epoxides, vinyl ethers can be readily used in cationic curing. I have a selection of these are listed on the slide. So you can have monofunctional vinyl ethers, and this, as you can see, is a very single vinyl moiety, or difunctional vinyl ethers, and a really simple example is this molecule. And you can have a quite wide range of these materials. These were very popular some time ago, maybe 10, 12, 15 years ago in cationic curing. They've fallen a little bit out of favor over the past few years, not because of any restrictions on their chemistry, just that there's not as many sources, commercial sources of these materials. So while they're useful, there's not they're not readily available as some other materials. Here's a comparison between epoxy systems and vinyl ethers in cationic curing. You get, while epoxies you have minimum shrinkage, you get more shrinkage using vinyl ethers. Both have post-cure. However, where vinyl ethers really shine is that they are extremely rapid cure. So if you need to have a fast cure, and epoxies sometimes can be quite a bit slow, vinyl ethers will really help boost the cure time. Epoxies tend to be low cost. However, vinyl ethers, and I think that's in due part to their not being as readily available, tend to have a little bit higher cost. I like to compare the relative rates of reaction and conversion, of the different monomer types you may be familiar with in UV curing coatings and inks and adhesives. Here on the y-axis, we have percent conversion, and of course on the x time. We see that the highest conversion and fastest reacting is acrylate systems, so free radical acrylate systems. Vinyl ethers are actually quite close to those in both conversion and reactivity, and that's followed by cycloepoxides, then methacrylates in free radical, and finally simple non-cycloaliphatic epoxides. Going back to the formulations, we have additives that are commonly used, such as pigments. It could be inorganic, organic, fillers, just to lower the cost of the formulation. And you may need the foamers, flattening agents if your coating's too glossy, wetting agents, and slip aids. One thing to note with cationic curing is it's best to avoid the use of basic or highly acidic materials. As you can imagine, if it's very basic, you have your cations in the system, you're going to get curing in your container. If it's highly acidic, it'll quench your reaction. Another common component in formulations are hydroxy compounds, and these could be alcohols, polyester polyols, castor oil, hydroxyfunctional vinyl and acrylic resins, polyether, polyols and glycols, cellulose resins like CAB, and phenoxy resins. These are commonly used to improve cure speed, flexibilize your cured photopolymer, lower the cost, modify the viscosity, improve the cross-linking, and with these, primary hydroxyls tend to work best for that. Finally, let's take a look at what cationic photoinitiators are most commonly used in cationic curing. Likely the most common photoinitiator are sulfonium salts. These are available with different counter ions, either PF6 or SBF6, and they're typically supplied as a mixture. And you can see here at the center of the slide what we mean by a mixture. So you get basically a monomer or a dimer of the system. Both work well, and both are commonly used. The mixture is commonly used successfully. These are frequently available in a solvent. These sometimes can be difficult to blend into your formulation. So very commonly you'll see these available for sale as a liquid. And the solvent used most often is propylene carbonate. In addition to sulfonium salts, iodonium salts are also relatively commonly used in cationic curing. These tend to be a little bit less reactive than sulfonium salts. They're a little less thermally stable than sulfonium salts, but they give excellent depth cure, especially when used with anthracene or thioxanthone derivatives. I'd like to talk about anthracene, the use of anthracene derivatives just a little bit, because I find these very, very interesting. On this slide, I have the structure listed there, and this is known as UVS 1331. And the way anthracene derivatives work is that they absorb longer wavelengths of light and transfer that energy to the photoinitiator. These can dramatically accelerate cure speed and also enable curing of thick coatings. Here's how the anthracene derivatives work. This is a mechanism was proposed by Jim Cravella a few years ago. And here we have in the mechanism, we have our sensitizer exposed to the UV energy. It moves up to a higher energy state. It reacts with our photoinitiator, transfers that energy, and you now can form your polymer quite a bit easier than you would otherwise just trying to rely on the initiator and the UV light. Here's a great example of how anthracenes can accelerate cure speed. In this experiment, we have cure time on the y-axis, and these are in minutes, 5, 10, and so forth. And here we have the amount, or parts per hundred, ppm, parts per hundred of the anthracene derivatives. So let's start out here at ground state. Here we have at the start we have no anthracene derivative in our formulation. In the red here is the sulfonium salt, and blue is the iodonium salt initiator. So we see that it takes 15 minutes for the reaction to cure under exposure of light, while 30 minutes for iodonium salt. However, you start adding increasingly amounts of the anthracene derivative. So here 0.5 parts, 1 part, 1.5, and up to 2. We see we dramatically speed up the cure. For the iodonium salt is probably most dramatic. We go from 30 minutes at no anthracene derivative at one part per 100 there. We have now down to a little less than 5 minutes for curing. So you can see how these could quickly, by adding just a small amount of anthracene, quickly speed up our reaction. Now we're not just limited to sulfonium photoinitiators or iodonium photoinitiators. Other materials that can fragment and generate cations can be used. So we can use diazonium salts, ferrocene salts, and so forth, dialkyl phenacyl, sulfonium salts. However, for the vast majority of reactions, it's really usually a choice between sulfonium or iodonium photoinitiators when it comes to cationic curing. I would like to now move from our discussion on the materials that are used in cationic curing to taking a look at different formulating strategies that we can use to get the performance we need when we move to this type of chemistry. It's one thing to know in theory how you can achieve certain properties or performance based on an understanding of the key chemistry. However, on a practical basis, that is not always easy to obtain. So in the next few slides, I like to cover formulating strategies or tips or hints on how you can increase the reactivity of your formulation, modify viscosity, modify flexibility, how you would cure thick films, increasing the hardness of your coat, and improving adhesion of cationic curing formulations. Let's look at formulating for reactivity. Cycloaliphatic epoxides will be again the workhorse material, and I've seen a report that if they're ester free, you tend to get highly reactive or more reactivity out of your systems. The use of polyols to make the reaction proceed faster, and here the optimal epoxy to hydroxy ratio appears to be around 3. You can add a UV sensitizer such as UVS 1331, and we discussed that a few slides ago. Use a low equivalent weight polyol such as ethanol, isopropanol, diethylene glycol, or tripropylene glycol. Of course, you can increase the photoinitiator quantity. That works up to a point, and then you get diminishing returns when using more photoinitiator. You can warm the formulation and or preheat the process with using IR or hot air. Again, take advantage of the epoxide reaction and using thermal energy to increase the rate of reaction. And you can work in a dry atmosphere, dry air. At times, high humidity will slow down your cationic cure. There will be times when you may need to decrease the viscosity. For example, if you have a certain application method like spray coatings, where you need a very low, or inkjet coatings, where you need a very low overall viscosity. You can do that in multiple ways. You can use a vinyl ether. These tend to work very well. Triethylene glycol divinyl ether, hydroxybutyl vinyl ether, and so forth will help lower the viscosity. However, I'd like you to note that while vinyl ethers are excellent in reducing the viscosity, they can have a negative impact on solvent resistance. You can also go to low viscosity epoxy diluents, aliphatic epoxides such as hexane diglycidyl ether. Limonene dioxide is commonly used to lower the viscosity, Denicol EX321. Note that epoxides are less efficient in reducing the viscosity than vinyl ethers, but they do show high solvent resistance and overall good flexibility. Other methods of formulating for viscosity and decreasing to a lower viscosity is use of simple alcohols. Ethanol, propanol are commonly used. Low molecular weight glycols, such as diethylene glycol or tripropylene glycol. Now, while alcohols are excellent in reducing the viscosity, they will negatively impact your solvent resistance. Another, and this is somewhat not obvious thing you can use, is simply add a small amount of water. I've seen reported that up to 10% can be added without changing the cure speed, adhesion, or solvent or water resistance. Usually you hear, and it's very commonly believed in cationic curing, that any water is bad for your system. It slows down cure. However, over the years on commercial systems, I have seen addition of usually not anywhere near 10%, 1, 2, or 3% water is specifically added to the formulation. This tends not only to speed up the reaction at times, it also removes some variability by having a high humidity or a low humidity day in your manufacturing facility. Constantly moderate your cure speed. So it sort of evens things out. So what if you want to change the viscosity of your formulation, but you don't want to decrease it, you want to increase it? For example, you're using a screen coating. You can add cellulose acetate butyrate, or CAB, to your system, epoxy novolac resins, epoxidized polybutadiene, or highly viscous polyols. All these have been used over the years to increase the viscosity of your UV formulation. There are multiple ways you can formulate for flexibility. For example, addition of a triol at an epoxy to hydroxy ratio of 3:1 to 6:1 will increase your flexibility of your coating or your ink. Caprolactone triols and propoxylated trimethyl propane is commonly used. You can use modified cyclophatic epoxides. If you recall, at one of the earlier slides when I was talking about cyclophatic epoxides, I illustrated some of the structures, such as siloxide 2081, for example. You can use aliphatic epoxides, such as Epilede PB series, epoxidized polybutadiene, epoxidized oils, for example, soybean oil, castor oil, or a polyol like polycaprolactone. All of these have been used successfully in cationic curing applications. If you need to formulate for in-depth cure, so meaning very thick films, there are several ways you can do that. The most common approach is to use anthracene type derivatives such as UVS 1101 or UVS 1331, and these are very efficient in thick films at a concentrations up to 0.3%. So you add a very low amount and really get good through cure. Again, we covered this at a slide a little bit earlier. In addition to anthracene type materials, ITX is used. However, the effective concentrations are usually lower than 0.1%. Now, surface cure can be improved when you're going through cure by using a hybrid system, like an acrylate blend, and more about that using a hybrid systems a little bit later in our webinar. If you want to formulate for hardness, some of the ways you can approach that is by increasing the cross-linking. So using a commercial cycloaliphatic epoxide polyol blend, different types of polyols. You can increase the T sub G. You can mix in reactive resins such as epoxy novolac resin or highly functional glycidial ethers. And finally, you can post-bake your cure. So after you coat, you expose it to UV light, you just place your coating in an oven, post-bake it, and that tends to increase the hardness. What if you want to modify the tensile strength of your coating? In this series of experiments, we have here on this chart on the y-axis tensile strength in megapascals, and on the x-axis elongation in percent. So let's starting off with our workhorse cycloaliphatic epoxide, and in this case it's our old friend siloxide 2021P. It is a roughly upper 20s, maybe 28 or so megapascals in tensile strength, and elongation a little bit less than 1. If we add into the formulation PCl 303, and PCl 303 is part of the Placel series. So here we see the base molecule here with a little bit longer chains designated different Placels. So we add 5% of this material in, then 10%, 20%, 30%. We see a dramatic increase on going from less than 30 megapascals to almost 70 megapascals in strength, with a corresponding increase in elongation. So if you want to modify tensile strength, just adding a small amount of Placel materials can be exactly your solution. And finally, if you want to increase the adhesion of your coating ink, or of course your adhesive, there's a number of ways you can go about that. You can use a modified cycloaliphatic epoxide. You can use different types of aliphatic resins such as hexane diglycidial ether. Vinyl ethers have a really strong ability to not only reduce viscosity but maintain the adhesion. And I've seen reported that using PF6, so sulfonium salts, as a photoinitiator rather than antimony salt will also improve the adhesion of your cure coating. So now that you've had a good overview of the mechanism, the materials, and different ways you can work with cationic curing, why would you choose cationic curing over free radical curing? There are advantages and disadvantages to both systems, and we can see that here on the slide. For free radical curing, you have a wide variety of raw materials In cationic curing, it's much more limited. Though that has been changing over the recent years, and that is increasing, but it's still nowhere near the number of free radical materials. Free radical curing is inhibited by oxygen, so the oxygen in your air will slow down or even stop your curing. You have no inhibition by oxygen when you're using cationic curing. It's, as you saw when we had the mechanism, oxygen just can't play a role in the cationic cure. So that's a really good advantage. Free radical curing is not inhibited by humidity or by basic materials. Potentially, cationic can be. You get full cure in seconds for free radical. Cationic cure may take hours in some cases. This is not necessarily a bad thing. It's just something, and there may be some advantages why you want to have a slow cure, but it is there. You work with it. Free radical curing can suffer from shrinkage. This tends to be sometimes quite high, 10 to 20%. Cationic cure, because of the mechanism, you get potentially dramatic, or in some cases minimum shrinkage, which results in greater adhesion for cationic curing. You get depth of cure is greater in free radical, unless you're using something like an additive there in cationic curing. And overall, UV-EB market share has been pretty stable at around 90, 92, 94%, while cationic cure is the remainder 6 to 8%. So I view these as just both very good tools, but they're different, and they have their strengths in different applications. And because this webinar is focused on cationic curing, I like to just bring up why in my exposure to and working with cationic cure over the years, it's these three reasons: not lack of oxygen inhibition, low shrinkage, and greater adhesion, which has drawn a lot of formulations systems to use cationic curing preferably over free radical curing. I'd like to move from our overview of the materials and formulating strategies to an area of cationic curing which I find very exciting and also very useful from a practical sense, and that's hybrid systems. Hybrid systems is the name given to the use of free radical and cationic polymerization combined in UV curing in order to get improved properties. So as the name implies, you're using two different types of chemistries to get results or performance properties that you can't achieve with just one of those by themselves. The improved properties usually come about from the achieving an interpenetrating polymer network, or IPN. And an IPN is two or more polymer networks that are permanently tangled but not covalently linked to each other. So you can kind of visualize a ball of twine with two different types of twine. And we actually see that there at the bottom, a simple cartoon, red and blue there. So polymer chains like this are very tangled up with each other. Two different processes can generally occur. You can have the polymerization of two components that are both simultaneous and independent to form this entanglement. Or you can get initially one polymer is formed first, it's then swollen by the second monomer, and that's followed by a second polymerization. So you form one chain, and the second chain forms later, which just tangles up the first one. A mix of acrylate and epoxide systems tend to produce an IPN. Here are some of the hybrid system characteristics. Hybrid IPNs can produce cured properties that are unique when compared to an individual acrylate or epoxide system. The final properties are determined by the monomer and polymer miscibility and compatibility, the polymerization method, the order of polymerization, cross-linking density, and reaction kinetics. So you see you have a lot of little controls you can change to fine-tune your final properties. The remaining epoxy cationic chemistry will continue to dark cure, which will result in a change of properties for some time after exposure to UV light. So you lock in your properties, and you can get a shift in those properties. And if you're have planned it well, you basically drift into the properties you really need after the exposure to the UV light is finished. You can get potentially higher acrylate conversion in hybrid systems when compared to 100% acrylate systems when you use a hybrid system. This is due to the delay in forming a rigid glass-like state. So that's delayed, allows more of the acrylates and methacrylates to react with the free radicals. What are some of the characteristics of hybrid systems? And I'm speaking specifically of free radical and cationic. Oxygen inhibition of the free radical component is frequently reduced, likely due to the viscosity increase as the epoxide component is polymerized. So this has been noted repeatedly that appears to be less, maybe not totally eliminated, but greatly reduced in a hybrid system. One thing to note and to remember is that urethane acrylates will inhibit cationic polymerizations. In addition to acrylate epoxy hybrid systems, other combination of materials can be used, such as thiolene, thiol epoxide resins. However, the bulk of hybrid systems, and we're talking about UV curing, tend to be acrylate and cationic systems. Here's some very interesting work that was done years ago by Christian Decker and his team on properties of various hybrid systems. In this series of experiments, we have, he was measuring the hardness, the Perzaz hardness, and exposure time. We see here a simple acrylate system, gave hardness roughly close to 240 or so on the Perzaz scale. Going to a cycloaliphatic system, the epoxide, much higher hardness. However, the combined system, so the acrylate plus epoxide, not only gave an increase in hardness, but it also reacted quite a bit faster. So we got an increase in reactivity and an increase in hardness in a hybrid system. In addition to IPNs, another type of hybrid systems have been recently studied and is very neatly illustrated here by work done by Ariane Hassa of at the time University of Iowa. And this is photopolymerization induced phase separation. So you can get phase separation can develop as the orthogonal chemistries between radical and cationic monomers induce thermodynamic incompatibility, and they separate. So instead of getting an IPN, you get separation. The photopolymerization rates play a significant role in determining the domain size and continuity of those domains. And an indication of phase separation is the presence of two different glass transition temperatures in the final photopolymer. So you get these small Verli domains, and they all dramatically can change your properties of your cured coating. Here's a really neat series of experiments on photopolymerization-induced phase separation done by Ariane Hassa while at the University of Iowa. In this case, he used two simple systems. He used a butyl acrylate and an oxetane, so DOX, here's the structure for that, and combined them and measured their toughness. We see here, and also at different energy levels, 10 milliwatts per centimeter squared, 100, 1500. If you look just using DOX, polymerizing that, you can see you're clustered here, no matter what the energy you have, anywhere ranging from roughly 0.15 to close to 0.4. If you go to a one-to-one system, we get a slight increase at the higher energy of toughness, but we go a ratio of 7 parts DOX to 3 parts the butyl acrylate. Here we see a dramatic increase, almost double or over double at the higher energy level due to the photopolymerization induced phase separation. So you can start dialing in some really interesting properties by taking advantage of that phase separation. What Ariane found that the balance between gelation and phase separation determines the final polymer nano microstructure, and also the light intensity can be used to control the rates of reaction. That will not only determine the time to get your gelation of your network, but also influence the final mechanical properties. So far in our discussion on the hybrid systems, we talked about using two different types of molecules to achieve the modification of properties we're looking for. However, you can also do that by combining both functionalities in one simple molecule. An example of that is cyclomer M100. I have the structure illustrated here at the top of the slide, and we see we have a cycloaliphatic system, and here we have a functionality that can react with free radicals. So these are compounds that contain both cationic cure and free radical cure on the same molecule. It reacts in a similar, this molecule, cyclomer M100, reacts in a similar manner to methacrylates for free radical cure, and the same for cycloaliphatic epoxide. So it reacts as though they were separate. This allows the preparation of a coating, ink, or 3D printed object that contains either unreacted epoxides or methacrylate groups, and these can then be available for further reaction after you do your first initial cure. So you can be very creative in your formulation using molecules like this. For those of you who are especially attentive and noticed that on the initial slide when I introduced hybrid systems, or actually one of the early slides on hybrid systems, I had some examples of 3D printing. And the reason I put them in is because hybrid systems are finding them very good use in 3D printing or additive manufacturing. It's that fast cure of the acrylate component followed by the slower development of the cationic materials during dark cure, which really gives some advantages when 3D printing. The desired result is that the early formation of the printed object, so you print it. If you're familiar with 3D printing, will know that first you print your object, but it's at what's called a green state. It's only partially cured. You then develop the final properties, physical properties, during post-cure. This will allow targeted mechanical properties that would be very difficult to achieve using either a pure acrylate or an epoxide system. So you'll find quite a few commercial formulations for 3D printing will make use of hybrid curing. I would like to end our webinar today with some examples of commercial cationic formulations. Now, as I mentioned, these are commercial, these have been used, but these are also all that have been publicly disclosed, either at conferences or in brochures, so forth. So the systems that I'll be illustrating in the next few slides have been used commercially. These are relatively older cationic systems. Obviously, state-of-the-art systems usually are not shared publicly, but we'll give you an idea of starting points or how cationic formulations would look like in the real world. The examples that I'm going to show are those for a laminating adhesive, a metal coating, a clear coating, flexo printing ink, and finally printed circuit board formulations. I'm not going to go into depth on any of these. I may point out one or two features, but it'll be mainly just to illustrate how these formulations actually look like when used commercially. Here's a laminating adhesive formulation. In this formulation, we just have, it's relatively simple, 3 components. 80 parts of siloxide 2021P, our workhorse cycloaliphatic, a vinyl ether, CHVE, and our photoinitiator. And this gave at a relatively low viscosity the lap shear that was required in this application. Here we have a much more complex formulation that was used in overprint varnishes for metal substrates. Why was it used? Probably because of the very low shrinkage and great adhesion helped that coating stay on that metal substrate. And in this case, we have our siloxide 2021P, and then followed by quite large amount of other materials, castor oil, epoxy novolac resins, 2 different types, polyester polyol, propanol, trifunctional polyol. Our photoinitiator was a sulfonium salt, and then a variety of additives like polyethylene wax, Teflon wax, and so forth. And here are the properties of that overprint varnish for the metal substrates that we just saw on the previous slide, the formulation. So aluminum, tin-free steel, and tin plate. We could see that we had a range in hardness, and range in range in MEK rubs, with adhesion being essentially perfect right across the substrates. And it should be noted that for those who've worked in metal substrates, materials like tin-free steel can be a challenge, and tin plate can be a challenge getting a good adhesion. Here we have a cationic UV clear coat that uses a range of polycaprolactone triols as the polyols at different weights, equivalent weights, and three formulations. And in this case, you see H difference in the reverse impact with the higher equivalent, the higher trial, 285 trial, giving a much improved impact weight, yet the smaller polycaprolactone trial. MEK double rubs is greatly improved. So by changing the polyol, you're able to dramatically change the performance of your final cured material. You're not only limited to clear coatings, you can also do inks. And here we have a range of inks: blue, or cyan, magenta, yellow, and black, all based on siloxide 2021P, using a polybutadiene resin and some oxetane in there for cure speed. And we're able to get a nice range of very effective inks that will be excellent for printing on metal substrates. And finally, I like to illustrate a printed circuit board coating, a PCB coating that was based on cationic cure chemistry. And once again, cell oxide 2021P was the material of choice to get that, but also limonene dioxide, epilede material, PCl305, and this gave a very good, effective, and commercial PCB coating. So with that, I'd like to thank you for your attention and for viewing this webinar on the basics of cationic curing. And if you'd like additional information or you'd like samples, please contact Tony Franklin at Nagase Specialty Materials, and his email is there listed on the slide. Again, thanks very much, and I hope you enjoyed the webinar.